This is the first lesson for Chapter 4, which is all about what we call torque and equilibrium for Physics 12. And in this lesson, we're going to take a look at something called equilibrium at a point. For this unit, this is our fourth unit now of physics. For equilibrium at a point, the key strategy for finding solutions is to balance forces. In this unit where we're looking at things being in equilibrium, we don't want them to move at all. We don't want to have any velocity. We don't want to have any acceleration. We don't want them to do anything but just simply sit there and just safely not fall down. So if your object is going to be in equilibrium and that acceleration is going to equal 0, then how do you achieve that? How do you get to the point where the acceleration is 0? And the answer is you just have to make sure that the net force is equal to 0. That when all of the forces act on this object, they don't add up to anything. They're going to add up to a big total of nothing. Now that is so important that it's actually called the first condition of equilibrium. We're going to see a second one in a couple of days, but this is the first condition of equilibrium, just making sure that all of those forces add to nothing. To accomplish that mathematically, we've got a couple of options, and this is really similar to when we were working with conservation of momentum and collisions just one unit ago. The best, cleanest way to go is to use a picture of vectors all adding up. That works awesome if it's going to make a triangle because we have good triangle skills. So that'll work great if there are 3 forces. If there are more than 3 forces, then you're going to be stuck working with components, making sure that there's no net force in the x direction and no net force in the y direction. Not quite as nice, but you'll have to do that if there are just too many forces. We're going to try them both out here today. So here's the first picture. You've got this, maybe it's a sign that's 25 kilograms and it's being suspended by a couple of ropes, maybe in an alley between a couple of buildings. And your job is to find out what the tensions are in each one of these ropes. That way when you were going to the hardware store to buy the rope, you knew for sure you were buying one that was strong enough. We're also going to see which rope's got more tension in it as well. So for this picture, my free body diagram for that sign would actually have 3 forces. There's the force from rope 1 and the force from rope 2, and then of course there's gravity pulling down on the sign itself. And that tension 1 is diagonal. It's a diagonal value at a 40-degree angle, and that's one way to talk about it. Or if we choose to, a different way to describe that, to parameterize it, we would say, is to talk about the x component of tension 1 and the y component of tension 1. And so we can either do those green numbers or we can do these black numbers here, whatever works best for us. Okay, we're welcome to try either method out. Now for this story, I'm actually going to begin probably the worst way. I'm going to do components and then I'm going to do the vector picture. Looking back, vectors is the way to go. There are only 3 forces there, T1, T2, and the mg. But I'm going to look at it from the point of view of components, just so you can compare and contrast the methods. Now, for components, you could say the ups minus the downs are equal to 0. I like to say the ups equal the downs. That way I don't have to put a minus sign in. So for me, the up would be the T1y, or you could call it T1 sine 40, and the down would be the mg. Going to the left, I have T1x, or you could call it T1 cos 40, and then to the right I have T2. And so when I set up my components method, I like to say, hey, my forces left equal my forces to the right, my forces up equal forces down, just so that I don't have to put the minuses in. And now, again, options. For the left force, it doesn't matter whether you'd prefer to call it the T1x or the T1 cos 40. Whatever works best for you. Be open-minded. Sometimes one way works better than the other. So that equation, that doesn't really tell me much. I can't figure out what T1 is from there. I can't figure out what T2 is from there. It's underdetermined. It just doesn't have enough math info in it. Up and down, I could either write T1y for the up, or I could write T1 sine 40, well, whatever makes me happy. And that's equal to the mg. But I know the m, it was like 25 kilograms. So I could actually start over on this side, and I could figure out how big that diagonal tension T1 is. I could even find T1y as well. But that T1 is useful to know, 381 newtons. Now that I know that, I can go back to the other component, to the x component, and say, hey, I've just learned that this T1 needs to be 381. And now I can complete this calculation and see that rope 2 has to be 292 newtons tight. And I'm done. I've found the answer. Rope 2, 292 newtons. Rope 1, it's got a little more tension in it. Hopefully it's a good strong rope. It has 381 newtons. So that's the component method. Not our favorite. We'll do it when we have to, and we actually didn't have to in this story. We could have just done this all at once with vectors. So I'm going to take that picture, just going to back up here and look at the free body diagram. I'm going to take those three forces there, T1, T2, and mg, and I'm going to add them all up, just one after another after another. And I'm not going to change color at all because it's not like collisions where you had an initial and final. It's just all right now. And I'm going to just keep connecting them together until I get nowhere. I like to start with the forces that are beautifully arranged on the page, like T2 or the mg, and then maybe draw the diagonals in last. That's just my personal preference. So I might do this. I might say, okay, there's an mg force down. It's 245. Rope number 2 pulls to the right with some value I don't know. And then rope number 1, again, just keep connecting, head to tail. Rope 1 pulls back up and to the left. And by the time I'm done, I get absolutely nowhere. And so that's my picture I'm going to go with. This one's actually pretty nice. It's not even worthy of the sine law and cosine law. We can actually just do SOHCAHTOA and Pythagoras. Now looking at the picture, it said rope number 1 has a 40-degree angle compared to things that are horizontal. So find the thing that's horizontal here. It's actually T2, and then put your 40 degrees in. That leaves 50 in the upper corner, a 90-degree angle, and it's great. From here, it's just some grade 9, grade 10 stuff. We can do SOHCAHTOA, find out how big T1 is. At that point, you could do Pythagoras, or you can do some more trig, and it's really quick. Like, look at the math there compared to the component method. So components is fine if you have to, but it's much, much nicer to use the vector method. Here's one where you actually have to use the vector method. Well, you can do the component method, but it's a disaster. It's like 2 equations with 2 unknowns that just seems to go on forever. But this one's actually pretty nice with a vector picture. This time both ropes are diagonal. They're both actually pulling up a little bit and pulling to the side, but not symmetrically. We're not going to find the exact same tensions in these ropes because one is a steeper angle than the other. So my free body diagram, I would have my 2 diagonal tensions. They're asymmetric, not the same value, and then I'm going to have my mg going down. Only 3 forces though, so I'm going to draw this as a nice little triangle. I'm going to start off with the cleanest looking force, the mg, and then the force you draw next really doesn't matter. So you just pick one. So there's my mg. I'm going to put in the T2 next, which was up at a 30-degree angle compared to the horizon. Got that in there. T1 doubles back up to the left, finishes the story off so that the whole triangle adds up to nothing. T1 had a 40-degree angle, but not compared to T2. It was compared to the horizon. So if you need to draw in a little reference line, go ahead and do that. And now you can start playing around with alternate interior angles, Z-shaped angles. This one here has to be 30, and then there's got to be a 50 up there. And we can play around until we know all the angles in this triangle. Remember, you do actually know the mg. The mg is that 245. So we've got a perfect setup for, looks like the sine law. Got a 70-degree angle opposite that weight for the 25 kilograms. We can find T1, and then we can go and find T2. Super nice, super fast. So go with that vector method if you can. As long as there are not too many forces, that's actually the way to go. Okay, so here rope number 1 is 226 newtons and rope number 2 is 200. I want to tell you what you cannot do in this question. It doesn't work back at the beginning of this question to say, oh, well, I think T1 has to be strong enough so that its vertical part can hold all the sine up. No, it doesn't take the full weight of the sine. And it doesn't even take half the weight of the sine. Because if you give half the weight of the sine to the T1's y and half the T2's y, yeah, you might balance the ups and the downs, but you won't balance the lefts and the rights. So you want to do it all at once with a vector picture like this. We'll let the math just unfold the way that it does. One final question for today. Here's one where we're going to have to play around with components, right, in order to get things to be balanced. This one says, find the 4th force that will achieve equilibrium. There are many ways to do this question, and I would like to just show you one. And there are others that work just as well. Right now, it is not in equilibrium. It looks like there's a lot more force to the right than there is to the left. And I'm thinking there's more force down than there is up. But there are a couple of different ways that you can actually get this one to work in order to find the final answer. Here's one. You could actually go and see what the net force is so far, right? Remember, it's not balanced right now, but you could say, out of those three, what's my net force? And then we'll worry about what the fourth force would be to make it all add up to 0. So that 40 newtons, that's diagonal. It's got a sideways component of 40 cos 20 and a vertical component of 40 sine 20. And the reverse is true, well, the same is true for the 68. It's got a sideways component of 68 cos 60, and then it's reversed now. It goes down with a vertical component down of 68 sine 60. So you could say, all right, component-wise, so far with just these three, in the x direction, I've got a negative 12. Okay, it's going left. And then I've got a positive 40 cos 20. It's going to the right. And a positive 68 cos 60. It's going to the right. And that all adds up to something that's not 0. It adds up to 59 newtons to the right. That is not good. We're going to need a force that pulls back with 59 newtons to the left. You can do the same thing with the y. You can say, okay, what's happening with the y's? Well, the 12 isn't causing any problem with the y's. It's only going sideways. But the 40 goes up by 40 sine 20, and the 68 goes down by 68 sine 60. That adds up to 45 newtons down. You don't want that. You want 0. So we need to balance this out with something that goes 59 back and 45 up. And you can go and begin from there if you want, or other people like to continue working with the net force so far, and they go, okay, well, here's the problem I've got. Right now, this question goes too much to the right and too much down. It actually has an overall force value that's not 0. It's 74.8 newtons, 37 degrees down, 37.2 degrees south of east. That's not good. I want to fix that. I want the net force to be 0. I want to put one more force in that finishes this off, right? Because that was their question, right? Find the fourth force that will get to equilibrium. And right now I know my net force is 75-ish newtons and 37 degrees south of east. I need a force that's going to go north of west. It's going to have to go back west by 59 and up north by 45. In fact, it's just the reverse. If you take the 78 number, but just reverse the direction, you've got it. That'll actually figure out how big the fourth force would need to be in order to balance everything out. And that's the end of the first day, just balancing forces at a point, preferably with vectors. If you have to, we'll do it with components, but it's nowhere near as nice.